we'll kick it off. And I'm pleased to introduce Dr. Tanya Harrison. Dr. Harrison is the Strategic Science Initiatives Director for Planet. She is also a professional Martian, having spent the last decade working in mission operations for NASA's Mars orbiters and rovers. She holds a PhD in geology with a specialization in planetary science and exploration from the University of Western Ontario, a master's in earth and environmental science from Wesleyan University, and a bachelor in science in physics and astronomy from the University of Washington. Tanya is an avid science communicator, having made appearances in a variety of platforms. She's also a great advocate for disability and STEM, and also inclusion and mentorship of up-and-coming space enthusiasts. Please welcome Tanya Harrison.
Great. Thank you so much, Vanessa. Let me share my screen here. Okay. Looks like that's coming through for everybody. So today I'm going to be talking about big data at a planetary scale, looking at both Earth and Mars. And part of this was inspired by a question that I get quite often from students, which is, how does somebody whose background is in Mars science get a job working on things on Earth? And that was something that I asked myself quite a bit when I was trying to figure out how to get a job at Planet in the first place, because I thought when I first heard about Planet, it seemed like a really cool place and I loved what they were trying to do. But my entire background was working on Mars rovers and Mars satellites and landslides on Mars. How was I going to translate that to a commercial Earth observing company? We'll talk a little bit about those transferable skills. So I realized that thinking about my skill set, I was a Mars expert, but I was also a storyteller via satellites. And the things that you look at in satellite imagery, when you're looking at a rocky body like the Earth and Mars, there are a lot of similarities. So as you're learning how to interpret those images, in my case as a geologist, the things that you're learning in that process are pretty transferable. And I figured I would tell a story here if you're not familiar with satellite imagery, for the non-geologists in the room. So this is a picture from the context camera on the Mars Reconnaissance Orbiter, which has been in orbit in Mars since 2006. It's a panchromatic imager, which means that we image at a bunch of different wavelengths, but we don't separate them into like red, green, and blue. So the image that you see is black and white. Now, maybe you would recognize from this, there's some craters here, there's some streaks of stuff, but if you're not a geologist, maybe this image is not particularly exciting and it's not really telling you a whole lot. So let's dissect this a bit. One of the things that we can do is look at the relationship of different things in an image to the other things in the image, and it will tell us when the order of operations were in terms of what things formed before what, how old is something relative to something else, how long has it been sitting on the surface, things like that. So looking at this from the standpoint of a geologist, I can say that this big round feature here is most likely a crater. But it looks like it's been buried by something. It doesn't look much like a crater anymore compared to looking at all of the other craters around it here. There's the outside of that crater. This area, if we looked at a context view of Mars zoomed out from this is actually in a volcanic region. So the stuff that buried this crater is most likely a lava flow from that nearby volcano. So that came through and buried it. Then this is another lava flow. And we can tell by looking at this really distinct margin along the edges here, it has this flow-like look to it. So millions of years later, another volcano erupted and formed this darker lava flow. We can tell that it was millions or maybe even billions of years later because this is really dark compared to this. So it means it's probably less dusty. And you'll notice that there's a distinct lack of craters on this lava flow compared to the stuff on the other side. When we're doing geology on other planets like Mars or the Moon, one of the ways that we date surfaces is by looking at the density of craters, and specifically the density of craters by a factor of their diameter, essentially. So the longer a surface has been sitting out exposed to space, the older it is, generally speaking. There's some exceptions. The more craters it will have and the more large craters it will have. So we can tell from that alone that this surface is significantly younger than this surface here. And now we're going to zoom in on this little feature, which hopefully you can recognize. Maybe this is a crater. This is a view from the HiRISE camera, also on the Mars Reconnaissance Orbiter, which is 25 centimeter resolution compared to 6-meter resolution that we had with the last camera. And we can see that this crater actually is on top of this old lava flow and on top of this old lava flow. So it postdates both of these. And we can see this light-toned stuff. This is the ejecta from when that crater formed. It's draped over the darker lava flow, so it has to be younger than that. And it's draped over the older lava flow as well. And if we zoom in on this area here, that's what's in this box, there's a ton of boulders. And usually when you have an impact crater, these don't necessarily stick around for that long in the geologic sense. They'll erode away over time. So it tells us that this crater is relatively fresh. It's either geologically young or it's been exposed to the surface for a geologically short period of time, because this still looks very distinct and very rocky. So this probably happened, again, millions of years after this young lava flow. So I started out my career working on the Mars Reconnaissance Orbiter, mostly on that context camera that we were just looking at pictures from. This is the little Swiss Army knife for scale here. And my job was to take pictures of Mars every day and then analyze them from the standpoint of a geologist. So is there anything interesting that's telling in this image that's telling us something about the history of Mars? And is the camera itself functioning properly? And this was the first image that I ever got to take of Mars with this camera. So it holds a special place in my heart. I'm really glad that it's a picture of something that's interesting. These are a bunch of pits on the slope of this volcano on Mars here called Arsia Mons. I'm really glad my first image wasn't just some broad, smooth area in the northern plains where there were no features to look at. And a lot of what we were doing with the Mars Reconnaissance Orbiter was looking at how the surface evolves over time, which isn't something that we had done necessarily intentionally with previous missions, because the thought before MRO was that Mars was kind of dead. We knew that there were dust storms, and we knew there were some seasonal changes in the polar caps, but the planet itself didn't really seem to be all that active. And MRO completely changed our view of Mars in terms of what we know is happening on the surface today. One of the things that we documented quite a bit of, both with Mars Reconnaissance Orbiter and with the Mars Global Surveyor spacecraft before it, were new impact craters on Mars. So this is a place where we had 2 context camera images, one in June of 2008, and then one of the same place taken 2 months later. And there was this sort of scattershot view of all these little impact craters. This is a higher resolution view with the HiRISE camera, so you can actually start to resolve the craters themselves, at least the bigger ones. But if we zoom in even more, the thing that we discovered with these with MRO that we had never seen with Mars Global Surveyor was that some of these impact craters were exposing this light-toned bluish stuff. So we actually asked another instrument on board MRO called CRISM, the Compact Reconnaissance Imaging Spectrometer for Mars, it's a mouthful, to image this blue stuff to tell us what it was made out of. We assumed it was ice for a lot of different reasons. I won't get into the geology, but CRISM was able to confirm to us that this was indeed water ice that had been exposed at the surface by the formation of these craters. We were also able to see a lot of other changes on the surface of Mars with MRO and sort of continuing the record from Mars Global Surveyor. So we could watch the polar caps change throughout the seasons. So this is the permanent polar cap. But then as you go from summer into fall and winter, you get a bunch of frost that deposits around the edges. And then as you go from spring back into summer, all of that frost sublimates away. It goes from solid to gas in the atmosphere. We also saw avalanches coming off the edges of the northern polar cap, which had never been seen before. Tons of new impact craters, some that exposed ice and some that didn't. And then these features here, so these dark streaks, these are called recurring slope lineae, and we think that they might be flows of really salty water, so brine, so salty that it's actually depressed the freezing point of the water to something like -70 degrees Celsius so that it can stay liquid on the surface of Mars during the warmest times of the year. So you'll see these little dots up here. It says spring and summer. These are forming in the summertime on Mars. And this was something that we had never seen before because we just didn't have high enough resolution cameras to be able to see it. We also had another camera on MRO called MARCI, the Mars Color Imager. And with that, we did this near daily global imaging of the entire planet to look at weather patterns. And so this is a sort of a globe projected view of just a single day's worth of Marcy coverage. And you can see some of the changes. So like here, the planet is really cloudy, for example, compared to this view. We can actually see some of the features on the surface. Here, we've got a ton of clouds over the large volcanoes. And when it comes back around, there's another volcano. Lots of clouds over Valles Marineris when it comes back into view. So around here. So we could watch these changes over time. And we've been doing this almost every single day from the beginning of the Mars Reconnaissance Orbiter mission in 2006, but also from the beginning of the Mars Global Surveyor mission in 1997. So we have almost a daily global image for all of Mars from 1997 to today, which is really unprecedented for any other place in the solar system. This is a really fantastic data set. So we understand the weather on Mars extremely well, and it's extremely predictable and repeatable because it doesn't have oceans. Ocean currents really make our weather complicated on Earth. So it's really easy to predict weather even on sort of a week-to-week basis on where there will be storms, how severe they're going to be. We know when global storms will happen, but we don't always know if they're going to happen that year. It's just kind of like tornado season on the Earth. We know when tornado season will hit in the Midwestern United States, but we don't know how severe it's going to be. But this data helps us with that. This is a sort of Mercator projection view of the entire planet of that Marcy data set. So you can kind of get an idea for just how dynamic the planet is. So you see a lot of clouds moving along up here along the edge of the northern polar cap. The white bluish clouds are water ice clouds, so very similar to the clouds that we have in the higher altitudes on Earth. And then places where you see some of this more wispy pink orangish stuff, those are dust storms and dust clouds. And pretty soon here, we're going to get to a global dust storm. So keep your eye on this part here. So what happens is you'll get these storms that spin off the edge of the northern cap, and then they come down, hit the southern cap, and then you basically lose the whole surface from view. We can see the tops of these tall volcanoes because they're actually so tall they almost poke out the top of the atmosphere. And then as the dust starts to clear, you can start making out the surface again. So it's kind of like a snow globe. You shake it up, the dust gets everywhere, and then it takes a really long time for that dust to settle back down to the surface. But I hope this gives you an idea. When you're used to seeing those static pictures of Mars, like just a global view, it doesn't really show you how dynamic it is, how much the planet is changing on a day-to-day basis. And this is something that we really didn't understand all that well until the Mars Reconnaissance Orbiter, because we had so much data coming back from all of these different cameras. But it takes a long time to send that data back from Mars. In order to make a near global mosaic of Mars with the Context camera, it took us from 2006, near the end of 2006, to March of 2017. So this is over a decade to get 99% coverage of the planet at 6-meter resolution. And a lot of this is because this is out of date from when I made these slides before, my apologies. A lot of this is the speed at which we can send back the data. So this is an internet test from my house the other day. Download speed of about 50 megabits per second, upload speed of 8.6. But there's a Twitter status that you can follow called DSN status that will show you the data rates that we're getting from different missions that are out in deep space. The data rate on this day from Mars Reconnaissance Orbiter was 1 megabit per second. So 50 times slower than my internet speed here in Washington, D.C. It also takes a long time for that data to get to us because you've got that light time delay. So the light time delay right now is about half an hour. It's a little bit longer than on these slides here. And this data rate is really highly affected by how close the Earth and Mars are to each other. So for the Context camera, it was a bonanza when Earth and Mars were really close to each other. We could take 300 to 400 images a day. And it was like basically a fight of, okay, how many of these can I fit in the buffer? How many can I fit in the time difference that we need for the camera to take an image, read out, and then be ready to take another picture? They couldn't be closer than 15 seconds to each other. That's how long it took to read the data out. But then it would get really depressing when Earth and Mars were really far from each other, like on opposite sides of the sun. You could take less than 10 images a day. I remember some days when we got like 3 images a day, and it was so heartbreaking because when you're trying to decide what 3 things am I going to image on the entire planet today, that's a lot of data triage, like trying to decide what you're going to do. And a lot of the limitations from this come from the Deep Space Network. We only have 3 sets of satellite dishes on the ground here on Earth that are set up to receive all of the data that are coming back from any deep space missions. I'm sure a lot of folks in this crowd know, but if you don't, there's a Deep Space Network Now website where you can actually go and see in real time what dishes are active at the different sites and what missions they're talking to. So here it's talking to Juno. Here this was talking to Voyager 1. This is talking to a bunch of Mars missions at the same time. There's also different sizes of dishes at these stations. So missions that are really far away, like Voyager, get to use the 70-meter dishes, the big ones. And then older missions and missions that aren't quite so popular in the public eye, where there's not such a need to get the data back at a high rate anymore, you tend to get relegated over time from the 70-meter dishes to the 34-meter dishes. And so a lot of the Mars missions, we use the 34. That's a sad day. Like every once in a while, when you get bumped up for some reason to the 70-meter dish, your data rate goes way up and you're like, oh man, we can take so many more pictures today. So I mentioned the concept of data triage, and this isn't just something we have to do with the satellites. We have to do this really, really heavily with the rovers as well. So you have to take a lot of factors into account when you're planning where you're going to take pictures on Mars. Every picture that you look at has been, generally speaking, intentionally targeted by a human to figure out where should we be imaging on Mars, given how many pictures we can take and what the conditions are on the ground right now. So if I was looking at Mars on this particular day, for example, I probably wouldn't want to shoot this area because it's pretty cloudy. So the signal to noise in the image might not be great. Another area I might not want to image. These areas look pretty clear. So this is Valles Marineris, the giant canyon system on Mars. And this one of the Tharsis volcanoes, for some reason, is relatively not cloudy compared to its neighbors. This is actually kind of unusual. And the northern polar cap is pretty clear. So these might be areas that I would focus my data on because I know that the quality of the imagery coming back would be a lot better than the cloudy areas. So when your bandwidth is limited, you need to prioritize your data collection. And the way that we do this on the rovers that we don't have the ability to do on the satellites is that the rovers have a bunch of onboard storage, basically solid state hard drives, and they can take a ton of images. And then every day it will send back tiny thumbnails, like 256 by 256 pixels. In the case of Curiosity, I can't remember if they're the same size for Perseverance. And then scientists will pick from those thumbnails which ones they want to send back now versus this is less important. We can send this one back later when we have higher bandwidth, or this image is blurry or not super useful. Maybe we don't need this image at all. So this is an example of some thumbnails coming back from Curiosity one day. If we were going to look at these, we could say, well, all of these 5 images look very similar. So I would maybe only need to send back 1 or 2 of them. This one was just of the atmosphere. I didn't really see any clouds, so maybe I don't need that. Maybe that one too. We'll skip that one for now. And then these are not really showing me a whole lot of the landscape, and maybe my priority for that day is to see the landscape to decide where we're going to drive or what targets we want to go after. So something to think about here is, how does data triage, having to be so selective of the data that you're acquiring and the data you can send back, actually limit the speed of insights that you're gaining from that data? So after I worked on these missions for a few years, I ended up coming to work at Planet. I started as the manager of science programs, and then eventually this year started as director of strategic science initiatives. And Planet really appealed to me because I heard about them when I started working at ASU, actually while I was working on the Opportunity rover, because they said that their goal was to image the entire planet every day to look for change. And I thought it was cool that there was a company that was doing that, because a lot of my job from MRO was looking at changes on the surface of Mars. And especially looking at Marcy, for example, looking at daily global imaging of Mars to look for changes. And we do this with these tiny satellites. So I'm sure everybody here is familiar with CubeSats. This is a form factor of one of the Dove satellites. And here's 2 of them back when we used to launch them from the space station, being deployed from one of the deployers there. So I said it took us 10 years to get global coverage of Mars at 6-meter resolution with the context camera. This is 1 day of coverage on the Earth at 3-meter resolution, so much higher resolution than we have for Mars. 1 single day of coverage from Planet data. This type of coverage blew my mind coming from Mars, where our data is so limited. I couldn't even imagine how much you could glean from this. And there's so much value out of this kind of data set. So the way we do this is partially because we have way more than just one giant satellite. We actually have a couple hundred, over 200 now, because we just launched 44 more satellites last week or so. And they orbit in this giant line scanner. So they're all kind of in a big chain. And as the Earth rotates beneath them, they're building up coverage line by line every single day. This is a little out of date because now our satellites are 8 bands. So it's red, green, blue, 3 other color bands, red, edge, near infrared. And then we also have this set of SkySat satellites, which is higher resolution tasking imaging. So instead of always being on like the doves, we actually have to point it somewhere and say, take a picture of this, take a picture of this. So the operations for that is a lot more similar to these Mars missions before, where you have a human in the loop manually selecting what you're going to be taking pictures of. But this can take pictures at 50 centimeter resolution. So getting us closer to that high-res camera on Mars and much higher resolution than the doves. And these can also record video from space, which is pretty cool. I just realized, thanks to that launch I mentioned last month, this is slightly out of date. We've now had another successful launch with SpaceX. So I think this is now up to 31. And we downlink all that data at 50 ground stations at about 15 different locations around the world. So we have a lot of access to satellite dishes to downlink that data compared to the limited access that a Mars mission would have through the Deep Space Network. So that's really helpful for getting that volume of data back down about 25 terabytes a day. And because we're just going to low Earth orbit, we're not going all the way to Mars. You can only launch to Mars once every 2 years, but we can launch to Leo pretty much any time. So we're not launching constantly because we don't need to, but we can hitch a ride anywhere we can. You know, Rocket Lab, SpaceX. We've launched with the Indian Space Agency before, ISRO. The earliest we launched with Rocket Lab. The earliest satellites launched from the space station. So we have a lot of options there compared to having to literally put all your eggs in one basket when you're going to Mars. And we've captured a lot of change on the surface of the Earth, and a lot of this happens incredibly rapidly, especially when we're looking at comparisons of how quickly the surface of Mars changes, other than things like weather. This is an example from last summer. This is off the northern coast of Ellesmere Island, so high Canadian Arctic. This was the last intact Arctic ice sheet, and it collapsed between July 26th and July 31st. In this case, the northern latitudes are super cloudy, and NASA tried to see if they could get a view of this with their Landsat satellite. But their satellite, when it flew over, it was cloudy, so they couldn't actually see the collapse. And so NASA pinged me and said, hey, did you guys manage to capture a view of this? And so I went to look. And because we have so many satellites, the satellites actually get crowded in the higher latitudes. So you get multiple passes per day from the doves. So on July 31st, we actually had 4 separate flyovers from 4 separate doves. 3 of those flyovers were cloudy. And this one, which was 10 hours after the collapse, or we had managed to constrain the collapse to a 10-hour time period. I misspoke there. We managed to capture this mostly not cloudy view. So you could actually see the collapse and then monitor this over the course of the next few days. Going backwards in time through like the 26th and earlier, you can actually start to see these melt ponds forming on the surface of the ice sheet. So this can give you a clue that, hey, maybe something is going to happen here. Since you're doing this type of imaging in the background with the doves, you're not actively tasking it like the SkySats or like the cameras on Mars Reconnaissance Orbiter. You can catch a lot of these changes sort of as they're happening rather than reactively. You don't hear that there's a change and then go image it. You can capture it as you're doing this daily background scan, which is pretty amazing. Another example of catching something kind of in the process was earlier last year in February. There was a massive flood and landslide in India, dubbed the Chamoli landslide. And this was something that made the news pretty quickly because it was rather destructive. It took out 2 hydroelectric power stations. This area is really prone to landslides to begin with. The Himalayas, obviously, you've got steep mountainous area where there's a lot of precipitation. But this landslide was particularly large and very mobile for the area, so the news was all over it. And the initial reports were that this was something called a glacial lake outburst flood, where you essentially have some kind of meltwater building up behind an ice dam. The pressure gets so high that it causes that dam to catastrophically burst, and you'll get this really, really destructive flood. But scientists started looking at planet data. This is a view from the ground of the flood as it was happening along the second area of the hydroelectric stations that got damaged. But since planet data goes out into our user interface, basically as soon as it's done being processed, researchers can go in there and do this data analysis in real time. So Dan Sugar is a professor at the University of Calgary who specializes in landslides, and he does a lot of real-time analysis of planet data and other Earth data sets like Sentinel-2 on Twitter, which is really amazing to see. And so he actually started looking at this area within a few hours of the flood starting. And he said, I don't see much evidence of a glacial lake outburst flood, a GLOF that is here. And so he tagged in a bunch of other landslide experts, and they start chiming in. Here he's replying to someone else. I didn't include the original tweet here. But he was able to say, no, this wasn't actually a glacial outburst. This was a glacier that was hanging off the edge of a slope that detached, fell about 2 kilometers straight down to the valley floor. And the heat of friction of that ice just smashing into the floor caused it to essentially instantaneously melt, mixed with the debris that was already on the ground. So, mud, creating mud and mixing with all this dirt. And it triggered this massive flood that then went down through the valley. So then this other scientist came in and started making 3-dimensional views with the data, analyzing, yep, looks like this was a glacier that detached from a slope based on what they could see in the imagery. And purely by coincidence, we managed to capture 2 images in this background scan, so again, not actively targeted, that caught this landslide as it was happening. So this image shows the dust cloud being kicked up by the flood as it's moving through the valley floor. This is the valley floor here. It's a little bit of a trick of the eye sometimes topographically, so it kind of looks like it's a rise, but it's actually a depression. And the first power station is here. The second power station is down here. This is the one that we saw the ground view of. So this was 10 minutes after it started, before either of the power stations had been destroyed. I'll pause it on the second view here. The second view is after the first power station was destroyed, but before the second one. And these images were taken 27 minutes apart. So we were able to really distinctly characterize the timing of the events of this flood by looking at the satellite imagery. As this was happening, Dan Sugar and some of those other scientists that he had tagged in on Twitter were messaging us with coordinates, asking if we could get SkySat imagery here. And so we got it as quickly as we could. And we were able to see exactly where that glacier detached from the slope. So before the flood, all of this area would have looked like these. This is just snow-covered glaciers on the side of this mountain. This area here, this is where the glacier detached, fell down the slope, smashed into the valley floor, and then the flood moved down this direction. And so Dave Petley, who's one of the folks that was tagged into that Twitter thread, noted that getting data immediately like this lets scientists analyze these events within a few hours rather than a few days. And this is really important for the geologic sense, understanding what the hazards are in these areas, understanding if there are going to be future hazards in these areas. And it also helps with first responder efforts because you can go in and see where is the greatest amount of damage, where are we going to need to deploy resources quickly. Another example that we've seen recently is illegal sand mining. And this is something that tends to surprise people if they're not familiar with it, because you think of sand as being quite copiously available around the world. There are beaches all over the place, right? But sand is really critical for making concrete. It's part of the binding agent in concrete. And the type of sand that you need to do that is not the kind of sand that you'd find in a place like the Sahara Desert. It tends to be sand that you dredge out of rivers because you need it to be kind of angular and globby from a geologic sense. And so there's actually a whole illegal sand mining industry in certain parts of the world. And it's led to journalists being murdered. It's led to these sand miners being murdered. There's essentially mafias that have formed around these things. And so if you're interested in learning more about this, there's a Vice documentary called Vanishing Sand that's available for free to watch on YouTube. It's really, really fascinating if this isn't an issue you're familiar with before. But Chris Hackney here, who is at the University of Newcastle, was using ground-based data and planet data to look at measuring changes in river elevation from this illegal sand mining activity. And so they could actually look at the elevation change in the rivers in this area and then map out these dots here are every place that you could see a mining vessel. And so you could see that the places where there was erosion happening in the river were places where this was not natural erosion. These were mining vessels that were actively dredging sand out of the river. And this can affect the hydrology in the area in ways that it affects the risk for floods nearby the river. So this puts local people at risk. It can also affect the ecosystems, both in the immediate area from flooding and downstream, because you've changed the dynamics of how this river flows. So this can cause a lot of problems in both the near and the long term. He was also able to measure the size of boats in the satellite imagery, and from that calculate how much volume-wise can each of these boats transport. And if we count the number of boats per day in different parts of the river by looking at boat density here, can we figure out how much sand is actually being extracted from the river? And you can do that on, a near daily basis with this kind of data, which is just mind-boggling. And from this, he was able to plot that at least in the Mekong River, there's significantly more sand being mined than nature is replenishing. And obviously, if you're removing more things from a natural system than you're replenishing, you're going to run out of that resource at some point. So right now, this is a completely unsustainable practice. And the mass of sand that's being removed from the river is increasing over time. So this is something that's really becoming a problem. We've also been able to see a lot of the impacts of COVID-19 from space as well. So this is a view of Venice. And I think you probably saw some of the viral stories that the canals of Venice had cleared up during COVID. Some of those things, like the videos of porpoises or dolphins, were not real. But the canals around Venice actually did clear out quite a bit during COVID. And a lot of it was due to the lack of boat traffic, because you had a lower level of turbidity in the water. The water itself was not churning around so much. And because you had that go down, the amount of sediment that was moving through the water was also lower. So the water looked clearer, both, if you were on the ground and from space. So this is before the lockdowns, and this is after. And if I flip between those, you'll notice you can start to see more of the features under the water, especially like here and over here. They become a little bit more distinct. So you can actually do some what's called bathymetry. So you're looking at the features under the water, and you can actually start to do that from space. They were also able to look at this and get an idea of the amount of suspended sediment, like calculate the amount of suspended sediment that was in the water over time. And if we zoom in, this is a pretty striking example. So this is October, before the lockdowns really started. Tons of boat traffic. This is sort of a typical day in Venice. And this is just after the lockdowns came in. You'll see that the water looks completely different. And that change is almost entirely from lower levels of turbidity. There's less boat traffic, and so you're not churning up the water quite as much. Some of it is also a little bit of a difference in the illumination angle, because obviously the sun has moved. So it leads to a little bit of a color difference, but most of what you're seeing is just the water is calmer when the boats aren't there. I'm sure you saw all over the news pictures and video of airplanes piling up at airports. This was also something we could see from space. So this is an airport in Victorville, California, especially if you watch the runway here. This is before, on March 20th and March 25th. Tons of airplanes stocked up at this airport as everything shut down. Another thing you can monitor from space is the amount of oil that's sitting in oil tanks at different places. And you can use this to keep an eye on things like how much oil do we have stockpiled in different places, and how is that going to affect oil prices? And you can do that because the tops of these tanks actually float on top of the oil. So the deeper this shadow is, the less oil is inside that oil drum. So this is March 21st, March 31st, April 18th. So you can watch how these are changing over time. So here between March 21st and March 31st, it looks like these sank, so the oil level went down. And this looks like it decreased even more in some of these. But a lot of that is just visually inspecting images. We can also apply the power of things like machine learning and artificial intelligence to extract more information out of this imagery than you can do just from a human eye looking at this information. Now, when I was working on planetary data, we didn't really have that much data from Mars. And so big data and the idea of using automated analysis hadn't really kicked in, and even right now hasn't kicked in all that much for planetary data sets. My PhD involved manually looking at 70,000 plus images to map out where every single gully was on Mars. And by the time I was finishing my PhD, machine learning was starting to become a bigger thing in the field of remote sensing. And I remember one of the engineering professors at Western coming to my defense and coming up to me afterwards and saying, "Oh gosh, I really wish I could automate this for you." We tried, and it turned out to be very difficult. But on Earth, we have so much data, and we have data from different sources that we can combine together to do some really novel applications. And one that I didn't even imagine we could do with an optical satellite is air quality monitoring. Usually, air quality monitoring requires really big, expensive, hyperspectral satellites that are looking at very specific wavelengths of light in the atmosphere to tell you the concentrations of things like methane or CO2 or whatever other pollutant you might be looking at. But a group out of Duke University actually looked at the haziness factor of images and combined that with air quality monitoring levels on the ground to be able to create a machine learning algorithm that can then predict, based on how hazy an image looks, what the air quality level on the ground is just looking at that. So they took in a bunch of images over Beijing, used something called a random forest regressor, which is a pretty commonly used thing in the field of machine learning. And from that, they were able to create these near daily maps of PM 2.5, which is particulate matter smaller than 2.5 microns. The masks that we're wearing for COVID right now are really good at filtering out particles of that type of size. Then they took this model and they ran it over a place, they ran it over Shanghai, where they didn't bring in the air quality monitoring station data on the ground to see how accurate it was. And they got really, really great results. The accuracy was like 89%, comparing it to the data that they had on the ground. So this is a really novel application that I didn't expect to see. You can also do a lot of humanitarian aid type work with this data. And obviously, this is not something that we ever do on Mars. So that this was not something that I had ever encountered before. But all the supply chain shutdowns from COVID really impacted the global food system. And so there was a lot of concern, especially in 2020, that certain countries might be at risk of famine. And so governments were mobilizing to try to make sure that wasn't going to happen. The government of Togo, which is right here, approached a group called NASA Harvest, which is NASA's food security arm, and asked them to make a countrywide map of cropland in order to figure out where they should distribute aid to farmers to boost food production so the country would be okay. And thanks to machine learning, Harvest was able to make this map and deliver it to the government in the span of 10 days. And this is what that map looked like. So everywhere here that is bright yellow is probably a farm. In Africa, this is particularly tricky to do in terms of mapping because the farms in Africa are smallholder farms for the most part. So these could be anywhere from like the size of a football field to the size of a suburban front yard. And they're very irregularly shaped a lot of the time. It's not these round pivot irrigation fields that you would see if you're flying over, the Midwest somewhere. So from this, they could see where are all the farms and where do we need to go to actually distribute aid to the farmers. I'll go ahead and skip this example for time since we're running out of time. But basically, having this high cadence global coverage provides the potential for insights at the speed of change. So on Mars, we're getting data back so infrequently relative to how quickly we can do it on Earth. We're learning a lot about Mars, but there's a time delay between when we get the data, how we analyze the data, when we can collect more of that data to try to really understand what's happening and how the planet is changing today. Whereas on Earth, we can be doing it in near real time because we have so much data. We can send the data back much more quickly, and we can act on that a lot more quickly as well. And then because we have so much more data for Earth compared to other planets, we really need stuff like machine learning and artificial intelligence to unlock the full potential of that planetary scale data set. And we maybe do have a level of data at Mars at this point. If you look at all of the missions, where applying machine learning can really get some additional insights that we haven't had yet from this multiple decades long experience of humans manually analyzing all of this data. So for anybody that's watching from like a machine learning aspect, I would challenge you to start thinking about what are applications that we could do, not just with terrestrial data, earthly data, but what could we do with the big data sets now that we have building up for places like the moon and Mars. So to come back again to the question at the beginning of how does a Martian get a job on Earth, the way that I tried to frame all of this is what are the skills that I learned working on Mars and working in mission operations for Mars missions that are transferable to something like the Earth? Number one, mission operations. Operating satellites has a lot of similarities regardless of what planet or other body that satellite is pointed at. So you understand how different systems work with each other. You understand the trade-offs of different things. You understand how to work on very tight time schedules. These are all really valuable. Also, satellite image interpretation. Because the Earth and Mars are very similar to each other, the geology that you learn on one planet applies a lot to the other planet as well. There's obviously a huge learning curve going from one planet to the other, but the basics of interpreting the images is very, very similar. So you can take that and apply it to multiple planets. Also, cameras and optics experience. So I knew how to operate cameras, and I knew a lot about technical details of designing cameras for space missions and going through what we would call a science traceability matrix. So what are the specs that you need for your camera to answer the science questions that you have for the specific thing that you might be doing? That type of experience and optics design, again, a camera is a camera regardless of what the camera is pointed at. Also, NASA speak. So a lot of my job at Planet before I transitioned into this new role was interfacing with NASA. So understanding their lingo, their jargon, all the acronyms, the structure of the different centers and who does what, that was all really important to bring into this particular role. And then again, for this particular role, working with scientists, a lot of what I do is engage with the research community, is knowing the research funding landscape. So what opportunities are out there? What things is NASA interested in funding right now? Where can I connect researchers to NASA opportunities or National Science Foundation opportunities? Or in Canada, what is the CSA doing right now? What is NSERC doing right now? What scientists are working on things in different areas where we could connect them to do different types of data analysis? So if you're trying to think the things that you're learning in like a space context, how can I take that and make it applicable to a job that I might be interested in? If you don't immediately see a way to make that connection, like if you're studying Mercury, how do I apply that to Earth or Mars or something? Think about how to frame your experience and the skills that you bring to a table in a way that is relevant to the jobs that interest you. Take a step back from the specific skills and think about the other skills that you gained while doing that. You've looked at satellite images of Mercury in this case. Well, did you use GIS software to do that image interpretation? That's great. You've got GIS experience. What other software packages do you use that might be relevant to the job that you're looking at? What other programming languages have you learned in the course of this that might be useful for the job that you're looking at? If you start to think about it that way, you'll realize that your academic experience is actually very, very transferable. It's just about reframing the way that you think of it. So with that, I know we're right at time, my apologies, but happy to take a few questions in the little bit of time we have left.
All right, that's great. If you don't mind going a little over, we can go into the networking time. I think there's no problems with that. Okay, awesome. So if everybody has any questions, feel free to put them in the chat, but we'll get started with some of the ones we already have. Arthur wants to know, what are the clouds on Mars made of? Shouldn't there be rain if there's clouds?
So the clouds on Mars are made out of tiny water ice crystals. There is snow on Mars, actually discovered by the Canadian LiDAR on the Phoenix lander, but it never makes it to the surface. It's kind of like if you see Virga in the distance on Earth, like that rain that's coming down, but it never actually reaches the ground. The same thing happens on Mars. The snow kind of goes between certain layers in the atmosphere and then freezes at a point and then just kind of freezes out into more clouds.
So we're not going to go skiing on Mars, I see.
You could, but you wouldn't see any snow. It'd be more like ice skating, I guess.
Oh, interesting.
Yeah.
So another question is, why is it important to study how old different specific formations and surfaces are relative to each other on Mars?
That's a great question. So a lot of it has to do with our longstanding interest in, is there life on Mars, which is intimately tied to, was there water on Mars? We know that we know that there's water there today. It's just predominantly frozen. But we want to look at the different geologic units on the surface and say, generally speaking, like, where was water interacting with these rocks and when was that water around? Because that will really tightly constrain when was this part of Mars potentially habitable.
Really interesting. And from Harsh, what softwares do you use to process the satellite imagery data, pivoting to your work at Planet?
So for Earth specifically, we use like a lot of custom tooling, but we do use some more widely available tools. Like GDAL is really, really common. So we use that for, like, map projecting images and doing other types of processing. For analyzing the data, we'll use things like ArcGIS, QGIS, Google Earth Engine. Google Earth Engine is not something that's used much in planetary science, if at all, but very, very heavily used in the Earth science community. So that was another, like, I knew how to use ArcGIS. I had to start completely over again learning what the capabilities of Google Earth Engine were, because it was something I'd never used until I came to Planet.
Oh, really interesting. And a question for me to end it off with the theme of our conference, innovation in space. What technologies are you really excited about for the next 10 or 20 years?
Oh, man. I feel like the space sector is changing so quickly. It's hard to predict what things are going to be like in 10 years. If we think back 10 years from today, like SpaceX, nobody would have believed that they could do the things they're doing right now. Planet was just sort of a glimmer in someone's eye. They were building CubeSats in a garage in San Francisco. And now we have rockets launching and landing all the time. We have people launching CubeSats constantly. It's just incredible. So I'm hoping, like, selfishly, the thing I'm most excited about probably is, like, seeing a crewed Starship launch. I would love to see that in the next 10 years. That might be overly ambitious, but we'll see. And I would love to see this sort of, like, low cost space view that we've really adopted for low Earth orbit kind of expand beyond that. We're starting to see a little bit of it pivoting toward the moon. Like, we're getting lunar CubeSats that are coming up online soon. I'd love to see that mentality expand to some of the other bodies in the solar system, so that we're not just having to have, like, billion or multi-billion-dollar missions to explore other planets, but maybe we can get these faster, not necessarily better, but faster, cheaper missions to at least get some data from these places that we rarely get to visit, like Uranus or Neptune or the moons of Jupiter, like any of that kind of stuff.
Yeah, so exciting. To finish it off, one last question from Harsh. He's a geologist and wants to know, if I don't have a strong background in computer science, where would I get started with machine learning?
That's a good question. I'm not a machine learning expert, so I'm not a great person to ask, but I would say if you have the ability to take some classes either at your university or find some courses online, I think it's something that's really exploding, and it's that thing that will help you kind of become get to the next level as a geologist. Image interpretation skills and GIS skills are still really important. Like, that's the core of things. But I think, like, for me, when I was in school, they weren't really teaching us as geologists how to do programming. And, like, the next sort of class after me would be the students that were learning how to program in Python. And I feel like for me, that's a huge gap in my knowledge. I'm not very proficient in any programming language at this point. I'm, like, embarrassed to admit. I used to be, like, decent-ish with a little bit of Python, but it's been years since I've used it myself. Now I feel like that next step is machine learning. So if you can find any classes, I would definitely sign up for them. I'd also recommend maybe looking at some of the work of, I'll put her name in the chat, but Hannah Kerner. She is a professor at the University of Maryland. She actually did a lot of machine learning work on Curiosity images when she was a PhD student at ASU while I worked there. And she's managed to pivot from this like combined geology and computer science background to now she works at NASA Harvest as their AI machine learning lead, working on Earth-based satellite data. And so it's a cool transition to see. Maybe just kind of take a look at some of the stuff that she's worked on, maybe read some of her papers. It might give you some pointers of things to look at.
Well, thank you so much for being here today, Dr. Tanya Harrison. Your talk was incredible. I loved seeing all of the planetary images, whether they were of Mars or of Earth. They were all fantastic, and I really appreciated having you here.
Oh, thank you so much. It was great to be back, and thanks everybody for taking time out of your day on a Sunday to join this conference.
If for all of our attendees, now is the networking time. So head on over to those expo booths. We have tons of incredible student space teams who are there to speak to you, tell you more about what they do, their research, and how you can get involved and learn from them. So I hope you head over there, and I'll see you at the expo.
Everyone,